Hello, welcome back. So we're now on to analysis of variance, or ANOVA for short. So I'm going to underline variance because that is the important word over here. So if we look at this example that we've got, just as in the previous class, we're going to use the return on the market as our independent variable. But now for our dependent variable, we're going to use the return on stock B. In the previous class, our dependent variable, it was the return on stock A. So we've graduated from stock A to stock B. And if we look at these returns along the horizontal and the vertical axes, these are annual returns. In the previous class, we had monthly returns. So that's why these returns are so much higher than the example we did in the previous class. So if we look at this dot over here, this dot represents a certain year. So let's see what happened in this year. The return on the market, it was 14%. And the return on stock B was 20%. So this was in actual fact the best year out of, excuse me, out of all of them. So we're going to actually be using this year a lot as we go through this slide. So each dot represents a year. And if you count up all of the dots, you'll see that there are 12 of them. So this means that we've got 12 years of data in this example. And I just want us to have a look at this over here, Y bar. So what is Y bar? We know what it is. It is the mean of Y. So this is the mean return on stock B. And we can see over here that the mean return is 9%. So we had some very bad years for stock Y. I mean, for stock B. So this year was the worst. It looked like it did about 2% there. That was the best year over there, 20%. So the mean return is somewhere in the middle between all of the dots. And so the mean return on stock B, it is 9%, and that's represented by this green dashed line over here. Good. So now what we need to do is we need to know all of these definitions. So let's start with this one, which is the total sum of squares. And for some reason, the abbreviation is not TSS, but SST. So some people say sum of squares total, so we can use either. So what is this? It is the total variation. So that's why I was underlying variance, because we're looking at variation. So it's the total variation in our dependent variable. So what is a good idea is, as we read the rest of this bullet point, is to look at the is to follow with the formula at the same time. So here is our sum of squares total formula. So what is it? It is the sum of the squared differences between the actual Y values. Remember, those are our actual Y values, and the mean of Y bar, the mean of Y. So if we take our year that we are looking at, this dot over here, what was the actual return in this particular year for stock B, our dependent variable? It was 20%. So we would put in a 20 over there for this particular year. And what is the mean of Y? It is 9%. So we'd have 20 minus 9 squared. And now that is only for that 1 year we're looking at. We need to do the sum of all of these square differences. So we'd have to do the differences between the dot and the green line for each and every year. Right, so it's such a mission. So they're not going to ask us on the exam, to calculate this, thank goodness. We just need to know what it is. So that's why we've got this long bracket here, because it's the difference between the actual return there and the mean return over there. Good. So now this total sum of squares, it's broken down into two parts. It's broken down into sum of squares regression and sum of squares error. So let's do the sum of squares regression first, which is SSR for short. So what is this now? Again, the variation in the dependent variable that is explained by our independent variable. And what is it? So let's do it in the same way as we look at the formula over here. It is the sum of the squared differences between the predicted Y values. So remember, Y with the hat on is the predicted Y value, and there y bar, the mean of y. So if we now look at our particular our particular year that we're looking at, when the market did 14%, what is the predicted return according to our regression line over here? So all we're going to do is go up there to the red line and go left. So our predicted return is 15%. And then the mean of y is 9%. So it would be 15 minus 9 squared. So that would be for our particular year, 15 there, the predicted return minus the mean of y, which is 9 squared. So again, we've just done it for 1 year. We would need to do that for each and every year and then sum up all of those squared differences. So it's quite a mission. But let us rather try and understand what they're talking about here. It's the variation in the dependent variable that is explained by our independent variable. So we can, because we've got this positive relationship here between the return on the market and the return on stock B, we can explain that when the return on the market is high, we can explain that the return on stock B is also high, 15%. So that is the explained variation in our dependent variable. And that variation is explained by our independent variable, the return on stock, a return on the market. Good. And then the other part of the total sum of squares is the sum of squares error, or SSE for short. Now this is what we looked at this one in the previous class. So this one is not going to be too bad. So what is this? This is the variation in the dependent variable that is unexplained by our independent variable. So what is it? We know this. Let's just do it in the same way again. It is the sum of the squared differences between the actual y values there. So yi, those are our actual y values, and the predicted y values. So y with a hat on, those are the predicted y values. So let us look at our year again. So when the market did 14%, then yi, which is the actual return on stock B, or our y variable, was 20%. But what is the predicted return according to our regression line? The predicted return was over here. We go up to our red line, our regression line, and go left, 15%. So the 5% there is the error. Hey, that's the error term that we spoke about in the previous class. So we're going to take that squared error term. So it's going to be 20 there, the actual 20 over there for the actual return, minus the predicted value, 15%. So it's going to be 20 minus 15% squared. And then again, we got to do that for each and every year and sum up those square differences. So it's quite a mission, but as we said, we're just going to know what this is. They're not going to ask us to physically calculate that. Thank goodness. Good. So the last thing we need to look at, which we've sort of discussed already, the sum of squares total. It's made up of the sum of squares regression there and the sum of squares error over there. So some people say that this SST, that is our total variation, is equal to our explained variation there and our unexplained variation over there. Good. So now we can continue, and we're going to now look at the ANOVA table. Now, this table, we've done some of it already on the previous slide, but there's a whole lot of new stuff that we're going to know over here. So let's get going. And we're going to start with this column first. So the first thing we're going to look at is the sum of squares. So over here, we've got the sum of squares regression. And remember what the sum of squares regression is? It is the variation in the dependent variable that is explained by our independent variable. And how do we work it out? I know we've done it already on the previous slide, but let's just do it again. It is the sum of the squared differences between our predicted y value and the mean of y. So it's good that we say it again so that we can learn it in this manner, right? The more we say it, the more we're going to learn. So then the degrees of freedom is 1, because the degrees of freedom for our sum of squares regression is actually the number of independent variables. And we've only got one independent variable, always with simple regression. That's all we're going to do at level 1, is just simple linear regression. So we've always got 1 degree of freedom. for our sum of squares regression. So now to get our mean square, and in this case, we're looking at the mean square regression here, all we've got to do is take our sum of squares regression and divide by the degrees of freedom, because mean we always divide by something. So we just divide the SSR by our degrees of freedom. So of course, SSR divided by 1 is just going to be SSR, right? So that is, so the MSR and the SSR are actually going to be exactly the same. And then let's not worry about this F statistic for now. We'll come back to that in a few minutes' time. Let us now go to the next one, the sum of squares error. Okay, so remember what the sum of squares error is. It is the variation in the dependent variable that is unexplained by our independent variable. And how do we calculate it again? It is the sum of the squared differences between our actual y values and the predicted y values. And now the degrees of freedom for this one is n, our number of observations. So in our example, we had 12, remember, and it's going to be -2. Why -2? Because we've got the intercept and we've got the one independent variable. So that's why it's n -2. So it's 1 for the intercept and 1 for the intercept and 1 for the independent variable. So that's n -2. And now the mean square error, what it is going to be is going to just be our sum of squares error divided by our degrees of freedom. Now, just before we go on to the next row, I want to put here /residual, because remember we spoke about this also in the previous class. The error term, we can also call the residuals, because I've seen in some of the CFA Institute practice problems, for this one, they sometimes call it the sum of squares residual. So it's the same thing, sum of squares error, sum of squares residual. Now they can use it interchangeably. So I just wanted to put it in there. So in case you see, in a table and in an ANOVA table, you see here residual and you think, where does that come from? Because we were talking about error, but it's the same thing. Okay, now the total, the sum of squares total is just the sum of these two. So the SSR plus our SSE is equal to our sum of squares total, or total sum of squares. So these columns, they sum vertically. So what is our total sum of squares? It is the sum of the squared deviations, the sum of the squared differences between our actual y values and the mean of y. So on the exam, what they can do, and we are going to see a numbers example on the next slide. They can give us the total sum of squares there, and then they can give us the sum of squares regression. So we can then work out the sum of squares error just by taking this one minus that one. That'll give us the sum of squares error. Right, so we will see that just now. So now the degrees of freedom, they also sum vertically, because we've got n over there, we've got -2 and +1, so that's going to be -1. So those also sum vertically. And then there's two more things I want to say about this table. The first one is this F statistic. We can see what it is. It's the mean square regression divided by the mean square error. So as we're going to actually do that, so what we're going to do what this is in a few minutes time. But I also just wanted to, I want to chat about this table. I want to ask you a question. Now, this is a very difficult question because, we did this so long ago, but this formula over here divided by n-1, can you by any chance remember what that is? Because that represents a certain formula that we did way back when. This is actually sample variance, because remember what sample variance is? Sample variance, or let's just call it variance for now. We take in the numerator the sum of the squared differences between the sum of the squared differences between the actual y values and the mean of y, and then we divide that by n-1, the number of observations minus 1. So just go back and you'll see there that this divided by that is the sample variance of y, of our dependent dependent variable. Now, the reason I'm saying this is because I saw in one of the CFA Institute practice problems, they asked us, they gave us the ANOVA table, and they gave us this number, and they gave us that number, and they said to us, what is the sample variance of the dependent variable? So it was quite a tricky question, because it's easy if we have the variance formula in front of us, we can quickly see, oh, that's actually variance, that divided by that is variance. But if we did it so long ago that we forget these things. So I just wanted to highlight that. Okay, so now what we need to do is the standard error of estimate. Now, before we look at the formula, I want us to look at the words first. What it is the standard deviation of the residuals. So this over here this is the mean square error over here. Now, so remember, and I underlined on the previous slide, this is ANOVA table, analysis of variance. So what is this? This is going to be the variance of the residuals. This over here is the variance of the residuals, or the variance of the error terms. So if we want the standard deviation of the residuals, what must we do? Standard deviation is what? It's just the square root of the variance. So if MSE is the variance of the residuals, or the variance of the error terms, to get the standard deviation of the residuals, all we need to do is take the square root of that MSE, and that's going to give us the standard error of estimate. Good. And we've put in here, the lower the better. So the lower the standard error of estimate is, of course, because it's error, the better the model is going to be. And then the other thing we need to know is this thing called the coefficient of determination, or R squared. Now, what this is, let's rather look at the words first, then we'll come back to the little formula. It is the percentage of the total variation in the dependent variable that is explained by our independent variable. So what is this then, this SSR? This is the explained variation. So the SSR is the explained variation, and we divide that by the total variation. And that's going to give us this here, the percentage of the total variation in the dependent variable that is explained by our independent variable. And we've got in here, the higher, the better. So the higher this is, the higher the coefficient of determination is, the better. Now, these are measures of goodness of fit. So what do we want for the exam? We want the SEE as low as possible, and the R squared, the higher, the better. And this F statistic is in actual fact also a measure of goodness of fit, and that we're going to come to just in a few minutes' time. We just need to go through our numbers example of the ANOVA table, then we'll come to our Fstat stuff after we've done this slide. Good. So now, this is like something we could get on the exam, where they give us the table. So I didn't physically go and work out all of these numbers, because I did this example in Excel, and we can just use Excel to automatically give us these things. So for example, with SSR, sum of squares regression, I didn't physically go and work out the sum of the squared differences between the predicted Y values and the mean of Y. I didn't do this 12 times and sum up all of the years. I definitely did not do that. Excel did it for us. So if we then look at what they could give us on the exam, is they could give us, say, this one, like I was saying on the previous slide, and they could give us that one, and then we might have to work out sum of squares error. So we just got to then subtract this from that, and that'll give us the sum of squares error. And then the degrees of freedom for our regression is just 1, because we've only got the one independent variable. And for the error, or slash, let's put in again slash residuals, error slash residuals, this is all the same thing. Sorry, my pen is just sticking a bit here. I'm not too sure why, but anyway, it's not too bad. So remember, it's n. So we had 12 years of data, like we said, -2, because it's -2 because we've got the intercept and we've got the one independent variable. So Our degrees of freedom for the error is 10. So now to work out the mean square, regression, all we got to do is take our sum of squares regression to divide by the degrees of freedom. So it's just 1. So it's just the same then as the SSR. And then for the mean square error, all we need to do is take our sum of squares error and divide it by our degrees of freedom, 10 there. So it's 3.614. And then beg your pardon, then I just wanted us to see that the total degrees of freedom, there's also sums vertically, because the 1 plus 10 is 11, like we said, and those two also sum vertically there. And here comes the Fstat. We're going to talk about it more on the next slide, but just for now, we can see it is the MSR over the MSE, so it comes out at 74. Right, so now the standard error of estimate, remember from the previous slide, what it is the standard deviation. It's the standard deviation of our residuals. So here we've got the variance, because this is a ANOVA table variance and analysis of variance. Here we've got the variance of our residuals. So to get the standard deviation of our residuals or of our error terms, we just take the square root of our MSE there. So it's 1.9%. So our standard error of estimate is nice and low. So it's looking good. Let's give it a tick. Our model is looking good. We want low error. Fantastic. And now the coefficient of determination. Remember what we do? We take the SSR, the sum of squares regression, divided by the sum of squares total, and it comes out at 88.13%. So that's also brilliant. So remember what this is in words. It is the percentage of the total variation in the dependent variable that is explained by our independent variable. And in our example, the independent variable, remember, it was the return on the market, and our dependent variable, it was the return on stock B. So this means that the return on the market is explaining 88% of the variation of the returns on stock B. Very good model. Okay, so now we've also need to learn something here, that with simple linear regression, our coefficient of determination, the R squared, is the same thing as the correlation coefficient squared. And remember the correlation coefficient from way back, its symbol is lowercase r. So if, for example, they tell us on the exam, the correlation coefficient, they're talking now about the correlation between the return on the market and the return on stock B. If they tell us that correlation is 0.9388, and they want us to work out the coefficient of determination, all we need to do is square that correlation, and that's going to give us our coefficient of determination. Right. And I put this in over here because I saw this in one of the practice problems, one of the CFA Institute practice problems, because if we are not given the correlation coefficient, well, it's not serious, because if they give us on the exam, if they give us the coefficient of determination, the R squared, we can work out the correlations, because the R there is going to be the square root of the R squared, as we know from maths. So if they give us the coefficient of determination is 88%, let's say they give us that on the exam, if we take the square root of that, that is going to give us our correlation between our dependent and independent variables. So this is the correlation between the return on the market and the return on stock B. Good. So now comes the F statistic at last. So what are we looking at here? We're going to do this thing called the F test. So what does it do? It shows or reflects if the independent variables together explain the variation in our dependent variable. So what is it? It's a test of significance of the independent variables. Now remember, we spoke about this in the previous class, that we can have more than one independent variable. So we've been using the return on the market, as our independent variable, but we can get other independent variables too, because other things will affect the return on stock B, not just the return on the market. So in the previous class, we mentioned the economy. So we could use GDP also as an independent variable. We could use inflation. We could use consumer confidence. Right. But the good thing with level 1, like we've said a few times, we only do simple linear regression. And then if it's simple, we only got one independent variable. So it makes life nice and easy. So I like to start here with the alternative hypothesis. And the good thing about this is that we're also going to be revising our hypothesis testing here. So the alternative hypothesis is, this is what we want to support, that the slope coefficient is not 0. We want it to be significant. So remember our regression equation, y equals our intercept plus b1 multiplied by our independent variable. So we're looking now at b1, the slope coefficient. What do we want it to be? We want it to be not equal to 0. So that's what we want to support over here. We want to reject this one. We want to reject this one, that the slope coefficient is 0. That's our null hypothesis. We want to reject that. Now, our F statistic, we've seen it in our ANOVA table. It's the mean square regression over the mean square error. Now, this is something that freaks people out, because when we did hypothesis testing, we said if we want to see if we are equal to anything, then it's two-tailed test. But with the Fstat, or the F test, it's only a one-tailed test. Now, why is this? This is because the MSR, the mean square regression, it necessarily increases relative to MSE. So this means that the Fstat can only be positive. The Fstat can never be negative. That's why we do a one-tailed test. But don't worry about all of that, detail and stuff and research and everything on it. We're just going to go with this. Right. So what we're going to need to do now is think back to hypothesis testing. What do we do with hypothesis testing? We compare our test statistic to the critical value. So here, our test statistic is the F statistic. So we're going to compare the F statistic to our critical F value at whatever level of significance they give us. And now with the critical F value, we get a numerator degrees of freedom and a denominator degrees of freedom. We will see an example on the next slide. Now, if we've got one independent variable like we do with simple linear regression, then our numerator degrees of freedom is only going to be 1. Okay, if we had, say, 3 independent variables, then our numerator degrees of freedom would be 3. But we only ever have 1 at level 1. So we're always going to use 1 degree of freedom for the numerator degrees of freedom. And then the denominator degrees of freedom is a number of observations -2, y -2, because we've got the intercept and we've got the 1 independent variable. So that's why it's n -2. So this is the deal. And this deal we know. So we're going to reject the null hypothesis if our Fstat exceeds the critical value. So if we can reject this one, if we can reject that, so let's put it across there. If we can reject the null hypothesis, then we can support the alternative. We can support the alternative hypothesis that the slope coefficient is not 0. And if that's the case, then the relationship between our independent and dependent variables, that's going to be significant. That's what we want. So let's see what we've got in our model. I think it's going to be good news because we saw a low SSE just now and we saw a nice high R squared. So I think we're going to be good here. So it says calculate and interpret the Fstat from our example using a 5% level of significance, and we've got 12 observations in our data set. So the alternative hypothesis is, I always like to start with this one. The alternative hypothesis is that the slope coefficient is not 0. That's what we want. And the null hypothesis is that it is 0. Right, so now our Fstat, like we've seen, it is the MSR over the MSE, and we saw that earlier also in our ANOVA table. Now we need to check out the critical F value. So remember, we've got the numerator degrees of freedom, which is just the one, because we've only got, there's always one, we've only got one independent variable, and our denominator degrees of freedom is the number of observations minus 2, so it's going to be 10. So now on the exam, what they can do is they can give us the whole F table, or maybe just like a partial F table like this over here. So the degrees of freedom for the numerator we find along the top row. So that is easy to remember for the exam, because numerator is always the top row. And this means the degrees of freedom for the denominator, that's going to be along the side row. So here is so what is our critical value going to be? This is our numerator degrees of freedom there along the top row, our denominator degrees of freedom there, degrees of freedom along the side row. So it's going to be this one over there, right? Not so. It's going to be 4.96. And don't let them confuse you on the exam. It's a one-tailed test. So we're going to use the 5% table, right? And just before we look at the conclusion here, I've seen in the CFA Institute practice problems that they often give us that information there, and they give us this over here because they often just want us to make the conclusion, because the exam, it's pretty conceptual. So maybe on the exam it'll be the same, but you never know. You're lucky. That's why I'm doing it all in so much detail. Or they might just ask us to work this out on the exam, or maybe just, what is the critical value? So we've done everything, but on the exam we're not going to do the whole thing here. But more likely they're going to give us this information and ask us to draw the conclusion. So here's our conclusion. So our Fstat of 74, it way exceeds our critical value of 4.96. So that means what? We can now reject the null hypothesis. So if we can reject this one, that's what we want to do. We can support that one. We can support the alternative hypothesis that the slope coefficient is not 0. And that means the relationship between our independent and dependent variable, it's significant at the 5% level of significance that we're using. Excellent. So that's the end then of that class. I hope it was helpful. So just study hard, and we're going to crack this thing, and we'll see you guys in the next class. Hello, it's Tim here again. I hope you enjoyed the class and found it beneficial. We have some classes available for free on YouTube, but we have classes for the entire curriculum. The classes that are not on YouTube can be purchased from us. If you'd like to purchase the classes, please contact us for the pricing, and I've put our contact details over here. You can purchase all the classes or certain readings that you would like. When you purchase the classes, we provide you with the slides and our notes. I've assisted hundreds of candidates pass CFA exams, and I look forward to also helping you through the CFA program. I've put in 2 testimonials in the slide over here, and we also have a testimonials page on our website that you can review. I look forward to seeing you soon, and all the best.